In the following lesson we present an application of the Areolar theory of elasticity. The intention is to show the power of the following resources. First, having the rotation integrated in the definition of strain. Second, the application of the correct equation of compatibility. Now we are prepared to approach the tri-harmonic plate bending. We consider a vertical section on a horizontal plate, and represent a point in this section by the complex number z, whose real part is x and the imaginary part is zeta normal to the neutral plane. X is taken along the neutral plane. The y-coordinate is also in the neutral plane and is normal to x. First of all, we expand the displacement field of the referred vertical section in Taylor's series in terms of z and z bar, up to the third power, with the intention of getting an approximate compatible field of displacements in the vicinity of the neutral line of a beam or of a plate. With the compatibility equations we eliminate the derivative of the real part of the complex shear. We also eliminate second derivatives in y of omega and theta, knowing that these functions are harmonic. The complete list of derivatives are listed in the paper. These are examples. The result can be cast in the expression. In the linear part we have Mindlin and the Navier's terms, while the cubic part represents the warping of the section. Fx represents a collection of derivatives in y. Supposing that all fibers of the plate that are parallel to neutral plane before bending will remain parallel after deformation of the plate, we can write the shear and rotation in a section of the plate in the form where V is the displacement normal to the neutral plane. F represents a function to be determined. At the upper and lower surfaces of the plate we impose the condition of zero shear, and at the neutral plane we impose equal rotations. Solving for dV dx and F, the horizontal displacement u of the section is given in terms of the rotation and shear in the areola situated at the neutral plane. Observe that the rotation of an areola of the neutral plane does not follow the rotation of the neutral plane due to the presence of the rotation due to the shear. We observe that we have the linear Navier's term and a warping term composed of a linear and a cubic components. We now have a field of horizontal displacements in the neighborhoods of the neutral plane that is compatible and satisfy the boundary conditions also. The shear and rotation of the section of the plate are given by. We first made a test with a beam. Applying Hooke's law, the stress at the beam section results. Calculating the resisting moment of a rectangular beam with height h and width b, we get. Observe that this operation can be made for a general section as well. Solving for the distributed load given above results. Applying to a simple supported beam with uniform load, we have for the shear force. And for the moment, from the shear force we get the shear strain at the neutral plane. Substituting into the equation of rotation of the neutral plane and integrating gives. Integrating once more gives the deflection of the beam. As the constants of integration represent a rigid body displacement of the beam, they are made null. The sag at the middle of the beam is correctly obtained. Correction factor is not required. Now we finally will approach to the plate bending case. Now suppose that we have a plate in the plane x and y. Zeta is the coordinate normal to the plane and w is the displacement normal to the neutral plane. We take for the displacements of a section of the plate normal to zeta the same expressions used for beams and calculate the fundamental strain modes θ, qsi, and gamma needed for calculated the traction st the section. As usual, we suppose the plate is in the plane stress state. That means that we use the modified Navier's lambda star elastic constant. We calculate the rotation of the neutral plane, adding the inclination of this plane to the rotation due to shear. For the shear strain we adopt initially the same used in Kirchhoff's plate theory, since it is compatible with the cubic displacement used for the section. From the plate bending equilibrium equation we refine the shear forces. And from the shear equilibrium equation we finally obtain the tri-harmonic plate bending equation. Changing from Lamè's elastic constants to Young's and Poisson's constants, this equation can be written in the following form, where the bending rigidity and shear rigidity R.